Hey guys, welcome back to the 3D optimization series. In parts 1 and 2, we talked about frustum culling and geometric merging. In this video, we are going to look at how occlusion culling works. The concept is again quite straightforward. As the name suggests, if any object is not visible to the camera, there's basically no point to spend computational energy to render it. This is the same reason that the insides of a 3D mesh are usually not rendered unless necessary. But it is usually quite tricky to realize which portion of a mesh is visible to the camera and which is not. Therefore, often programmers have to use their own logic to implement occlusion culling, or the game engine has to use raycasting to figure out if a mesh collides with any of the rays. Raycasting is the technique used in graphics rendering to send a collection of rays. These are usually represented by vectors from a single point in space. Let's call this point P toward an object that needs to be raycasted. Let's call this object O. A good idea to benchmark our occlusion culling is to first note down the total number of blocks rendered and then compare it with the total number of blocks rendered after we have implemented. To get the total number of blocks, we can use the spread operator to combine all the geometries and then just console.log its length. Now that we have this, let's move on to the code to implement the optimization. We place all the blocks in the terrain map matrix, and note that we are not placing the blocks on the HTML canvas of 3JS yet. We are just keeping those in memory because we need a reference of how the terrain map actually looks like, including the air blocks. In this function, we check two things. First, if the current block is on the edge. If a block is on the edge, there's no need to cull it because we want to show it. Second, we check if our block is surrounded by an air block on all of its sides. That means our block is an air block and there is no need to render it. The isFaceVisible function allows us to check if a face is occluded. How it does that is that it takes the coordinates of the current block and its neighboring block. If we check its usage, you can see that there are 6 usage for every single block that is placed on XYZ, and it's basically representing all 6 sides of a block, which is cuboid, which is a cube in our case. We also check if our neighboring block is of type air, and if our current type is not water, then our neighbor should be a water. In that case, it represents the block which is very next to a water body and it needs to be rendered. Finally, coming to our final code of this implementation. Here, we check if any of the faces of our block is visible, and if any one of the faces are visible, we need to render the block. Finally, by checking the type of the block, we push the block into its respective array. And that's it. We have successfully implemented occlusion culling. To check if we have made any progress, we can try to print the total number of blocks that we are rendering and compare it with the total number of blocks that we had recorded at the beginning of the video before we had implemented the optimization. Yes, we can now see that it is rendering only 85,000 blocks as opposed to the 200,000 blocks that we had recorded pre-optimization. That is around 57.5% improvement. We can also see by trying to go inside one of the hills that the insides of the hills are not rendered, as opposed to the previous version where if we try to go in one of the hills, you can see that the hills are completely filled with blocks which don't actually need to be there because we are not able to see that. I hope you enjoyed the video. If you found it helpful, please leave a like, and all the relevant links will be in the description. Thank you.